I would like to bring one point, which I think me and also Luca, I think, which is not fully discussed, and so we mentioned in the summary, is about metric affine theories. We did not discuss much on this, as what Perkachi has presented. So, well, the question I want to understand, so is, well, if I understand correctly, from at the end of the talk, you have said like, okay, you can have ghost-free higher derivative classical theory in the metric affine approach, but there are too many parameters, right? So first, one question is there a way to constrain these parameters? Second question is, well, why? Okay, well, in your from your talk, you are keeping the standard degrees of freedom, the massless graviton. We can introduce additional degrees of freedom as well, many degrees of freedom. I don't know what is the maximum number of degrees, maximum good number of degrees of freedom you can introduce in general, and is there any way to constrain them? If you can comment something about it.
Well, there are two ways to constrain. I think the most sensible way would be to have some symmetry, some additional symmetries, and that would be a constraint. Well, that would obviously restrict the type of terms that you can have in the Lagrangian, and it would also be radiatively stable, presumably, if you can respect the symmetry in the regulator. So it's something that would make sense also at the quantum level. But I'm really not aware of very many symmetries that you can impose in these theories beyond the standard one. So I think I mentioned in my talk a projective symmetry, which happens to be a symmetry of the Palatini action also, and others, but not of the generic action. So that brings down the number of parameters a little bit, but not drastically, let's say. And I really don't know of many others. I think this is something that is worth investigating. The other possibility is just to restrict the theory at the level of kinematics. So in the most general case, you have this the connection, which is given by, as Philip was repeatedly saying yesterday, it's given by the Christoffel connection plus a 3-index tensor. The 3-index tensor has 64 components, and there's huge room there. You can put many, many degrees of freedom in there, of any spin, actually, from 3 down to 0. And so you could then, instead of allowing this this tensor to be generic, you could say, for example, let's take it to be totally antisymmetric, or to have only a trace part, and things like that. And that then gives rise to restricted theories, obviously, because now it is the variables that allow you only to construct a smaller number of invariants. So, for example, Weil theory can be seen as an example of a metric affine gravity, where the non-metricity has a particular form. It is just given by a vector times a metric. So this 3-index tensor becomes has this special form. You can also do Weil theory in with torsion rather than non-metricity. I learned this from Prokopets some years ago. And there are various examples that you can give. These are basically the ways to restrict. Now, having said this, these theories generically will have this problem of ghosts, and so they are not unlike high derivative gravity.
Sorry for interruption. So the question, suppose you don't restrict the theory without any restriction, only put one restriction, which just ghost free, okay? Just put only this restriction. If you put this, how many maximum degrees of freedom you have in this, in most general metric affine theory?
That I'm not sure, because you see, we have only explored a 28 parameter family of theories. And obviously, even in this 28 parameter family of theories, you're not able to say which you're not able to list all of them that are ghost-free. So what I've seen is at most something like 6 parameter families of theories that are ghost-free. There may be more, but I cannot say for sure. However, I think that these restrictions, namely being ghost-free, is not radiatively stable, probably, because there's no particular symmetry that is attached to being ghost-free. And so I'm not sure what to do with that.
May I say something?
Sure.
Yeah. Well, Anand has a question. Is it related to?
If it's connected with this question, please go ahead, Ilya.
Yeah.
I have a question for Professor Herad, so I will ask him later, maybe.
Yeah, actually, because also we will switch to black holes in a few minutes, so maybe.
Yeah. Okay, so let's continue with this discussion. Then I will ask later.
Yeah, there were papers about this, what Roberto mentioned. So, for instance, the total amount of terms with torsion without non-metricity with 4 derivative R-square type is 168. It is paper by Stevenson, 1980. And there were papers also only with torsion in first order formalism by Nevenhuizen, Sezgin, Neville, and these people in 80s. And they found 15, family of 15 actions, which are ghost-free, but so you have at least 15 parameters. However, all these theories
just
are
only torsion, you said. Did you say only torsion?
Only with torsion. Yeah, only with torsion, without non-metricity. With non-metricity will be much more.
But
okay, you can construct many more.
Had fewer parameters.
I'm sorry, are these parameter free or there is some relation? How many independent parameters? You mean 15?
As far as I remember, 15, yes. Without non-metricity. But what's important is that how to construct these sections. So all these sections are of the Gauss-Bonnet type. This means that they don't contribute to the force derivatives in the metric propagator if you reduce first order formalism to second order formalism. And Valley made very good point about this a few days ago. See, he explains that if you want to have a normalizable theory, then it must behave, a propagator must behave by the end of the day in some special way. So this makes theory not free of ghosts. So you have ghosts. So you either have ghosts or you have non-normalizable theories. There is no way out in this fine-tuning parameters and so on. But you can construct plenty of theories actually. Okay. I have the same observation in some review paper in 2002, 19 years ago. So, so I thought about this. So I know this is true. I mean, okay.
So I completely agree with your statement. I'm not sure about 15 parameters with torsion, maybe, but anyway.
15 parameters with including torsion. I mean, you're talking about degrees of freedom or parameters? Just parameters.
No, right? I think he's talking about parameters in the
Lagrangian.
Lagrangian.
Yeah, parameters in the Lagrangian.
But exactly. If you consider only curvature plus curvature squared, it is less than 15. So they must have had some other type of
no, sure. They have something with torsion and so on. It says Nevenhuizen, Roberto. You can check this.
Okay. So what I know is the following: if you allow the most general form of connection with torsion and non-metricity, and you look at all the terms, all the operators that are of dimension 4, this means up to 4th power in tensor and maybe cubic interactions like in Young's derivative of tensor times tensor squared, and so on. You will have something like 900 parameters.
Yeah, should be a lot.
There's 500.
I would suppose this number.
Terms. There's 500 terms that are just tensor to the power 4.
But what's important is that all these theories with any choice of these parameters will be non-renormalizable.
or ghosts, or have ghosts. Yes, yeah. Well, now, of course, this is the standard point of view. So, you know, now recently we had all these he was saying that perhaps we can still live with this theory. So I'm curious to see what happens with this debate.
Yeah, there is another point I would like to ask you, Roberto. Well, in your recent short kind of review, so you're motivating this metric affine theories, connecting with particle physics. I try to understand it a bit, but it's not very clear. Maybe if you can give some more explanation about it. What is the like?
Well,
you're talking
people. I think somebody already.
Yeah, sorry. You're talking about these groups. There is SO10 particle physics group, then SO3 one. You're combining these two groups, and you're calling some very higher dimensional group like
Oh, you
SO1, and then you're relating isomorphism with SO77. So I just lost. What are these relations? I mean, physically. So why these are important?
You're talking about now about unification.
Yeah.
Yeah. This is something that I didn't talk about here, but it is somehow related to this. If you have gravity with an independent connection, then you may try to unify gravity with other interactions in the same way as, let's say, you could unify the weak and the strong interactions by just putting the two groups of the weak and the strong in a larger unified group. And you can try to do the same thing with, say, the Lorentz group of the gravitational connection and some other group that describes non-gravitational forces. Now, if you accept that non-gravitational forces can be unified in SO10 group, which is one of the candidate grand unified theories, then it is quite easy to put this together with the Lorentz group in some higher pseudo-orthogonal group like SO 11.3 or 13.1. So that is something that people, for some reason, don't consider or consider very little. I think the reason is that it's very difficult to construct a Lagrangian where you can tune a potential to go from the broken to the unbroken phase in the same way as you do in grand unified theories. So I think one can achieve a good description of the broken phase, but I really don't know how to go to the unbroken one. That's one thing. Well, the other thing that I can say in favor of this point of view is that actually the fermion that we see in the real world are a representation of such a higher dimensional pseudo-orthogonal group. So you can put every family of fermions into a single Majorana-Weil representation of SO13.1. What is it? 11.3. The group SO11.3 has Majorana-Weil representation. There are 64 dimensional, and you can put a family into that. So a single representation of that has both the Lorentz spacetime indices and the internal indices, and the group theory works out.
But all the symmetries from particle physics, won't they help to constrain more I mean, if you think gravity and matter system, so if they are useful to constrain some way the degrees of freedom in the theory.
The symmetries, you said?
Yeah, symmetries. Because you said you are searching for symmetries, right? So, well, the thing about metric affine theories is you anyway have to include matter. If you don't have matter, it's just vacuum. Then we get back to general relativity. So, well, I'm not, of course, if you have higher derivatives, of course, story will be different. Anyway, the matter is inevitable to put. I'm just speculating that if you, from the group theory point of view, you're combining the gravity symmetries and also the matter symmetries, and I'm just speculating if there exists some more fundamental way in this in this point of view, group theory point of view, to put some restrictions on degrees of freedom?
This is something that I think that perhaps a reason why people look at this with much suspicion is that there is this Coleman-Mandula theorem that says that in the folklore version of it, it says you can't mix internal and space-time symmetries. But if you look at carefully at what the Coleman-Mandula theorem says, you will see that that what I just said earlier does not violate the theorem. So I think there is room for further investigations.
Maybe before switching to black holes, if I can say something. So it's nice to see Kelly still with us, okay? Because we didn't say that during the conference. Actually, I feel bad for not saying that. But this conference, in a way, this workshop was partly motivated by the work of Stella, okay, Kelly Stella. So, and we should have said that, we forgot. But it would be nice to hear from Kelly, which is his opinion about this ghost business. Because you, of course, your paper inspired this workshop, but it would be nice to know your opinion about that.
Well, I wish it would go away. It's my opinion of the ghost. I don't know what to say. I think it's a serious problem. To the extent that one can take seriously John Donohue's point of view that maybe you can put the problem off for a while. That is to say, not have to deal with it at low energies, if they are, if there's a, I don't know if I agree with such arguments, but I listen to them. I mean, I looked a little bit myself at the kinematics of how to have ghosts run away and cause acceleration of other particles. It doesn't work for a single ghost emission, but it does work in multi-particle processes. Of course, those are then going to be suppressed. So I know Giadvali was of the point of view that as soon as you have a ghost, there's immediate catastrophe, the thing runs away. That doesn't agree with, for example, some computer experiments. I know that in Cambridge, people looked at systems, just simple scalar models with, first of all, of course, the ghost has to interact, right? Sure. It's a basic thing. And so that, by the way, is a comment that is related to what Philip Mannheim was bringing up, which about his work with Carl Bender. As far as I understand that was at a linearized version of Weyl squared gravity. So it's not interacting. It's purely the quadratic terms in the action, so linearized field equations. And then there's no problem at all because they don't interact. I mean, that's just a basic point one has to start with. They have to interact. Otherwise, there's no problem with ghosts. Just the separate non-interacting particles go about their own lives in their own portion of Hilbert space, and they don't bother anybody. So it's important that the interaction and the nature of the interactions is crucial. So if there is some way to have at least a respite from the ghost to suitably high energies, personally, I don't believe any of these higher derivative gravity theories are fundamental theories, but they might be useful as effective theories. And so, I mean, for example, in more recent work with Jean-Luc Lenners, we tried to look at cosmology from that point of view. And in fact, we arrived at a derivation of Roger Penrose's initial boundary conditions on the universe by requiring a finite action. So I think such discussions are, at least to me, interesting. And we made some arguments in there that you can push the ghost problem up to sufficiently high masses that at least you can trust this as an interim effective theory. I'm not going to go any further than that. I do think the ghost is a fundamental problem. You have to deal with it. And also personally, I don't really find much benefit in trying these infinite derivative theories, because I think that is basically just inviting, well, I think it was said, especially yesterday, that's inviting all sorts of problems further down the road. So I have a hard time getting excited about that as a problem. And personally, I'm more, attracted to such resolutions of what's the fundamental underlying theory is something like string theory. Mm-hmm. But so I know that Astrid Eichhorn and Alessia Platani have been looking at possibilities of some of these effective theories playing an interim role in a string context. I mean, string theory contains an enormous amount of stuff that you got to integrate out. The result of, in order to compare with the known theories, right? So if in the process of integrating that out, you develop an effective theory where the ghost problem can be put off for a while. By the way, a heterotic string theory in 10 dimensions produces R-squared terms, right, in its effective action. So the problem is not a million miles away from string theory. The issue, I should say, rather than a problem, because in string theory, it is a unitary theory, and presumably all these problems resolve themselves, thank you very much. So that's about all I can say about the ghost. Personally, I wish it would go away. But of course, nonetheless, having said that, maybe the virtual problems of features of the Weil-squared term have some bearing on such issues as corrections to classical solutions and so forth. So whether you can in one head take both points of view that don't bother me about the dynamical ghosts, but let's look at their consequences, for example, for structure of solutions. Is it possible to consistently hold those two ideas together in one head? That's another question. There's a folklore that you can't have virtual effects without dynamical effects, but that's just a folklore in quantum field theory.
Mike, may I make a remark?
Yeah,
I totally agree with you, by the way, about this ghost. But I don't know whether you were there when I had a discussion with GL Dwali.
Yeah. Yes.
I could imagine that the ghost means it's a negative metric object, so it's a negative probability of something.
Right.
It could be that the ghost is telling us that gravity as we know it, the Einstein-Newton action, has too many physical degrees of freedom, and you should remove some physical degree of freedom, which this effective theory does by adding a ghost that acts in the opposite direction as particles, as a kind of absent particle. Now, that's not good enough as a theory, and I think that we shouldn't say that this solves the ghost problem, far from it. But maybe it's an indication that we should search for gravity theories that have fewer than 2 graviton helicity degrees of freedom, and some part of that being removed. And of course, removing something out of a theory is much harder than adding something to it. So it's not a solution, but it could be an indication.
How do you see that, Gerard, in terms of the phase of the portion of phase states in Hamiltonian? Namely, these are massive degrees of freedom versus the massless ones in gravity.
Yeah. So the mass, it gives an extra suppression. So the massive graviton, it gives less of a contribution than the massless graviton. The massless graviton is dominating. Right. So to remove something which has less effect just reduces the effect of the single graviton somewhat. What it exactly means, of course, is very hard to tell, but I think it suggests, for instance, that you should search for discretized degrees of freedom for gravity, not the continuum, but let's have some lattice at the scale where this massive ghost sets in. Now, we don't know the mass of this ghost. It could be very light. It could be near the Planck scale. But at that scale, whatever it is, it could be that you have some sort of extra discretization, telling us that beyond that scale where discretization takes place, there are no gravitons at all. Something of this sort. Again, I'm not claiming this to be a solution. It's just an indication. Maybe we should be heading in that direction.
So you're thinking of something of a sort of a range-dependent suppression that depends upon the scale of interactions where the suppression would take place.
Yeah. Well, but you know what the effect of a lattice is on the field theory is it removes degrees of freedom which are small compared to the lattice size.
Mm-hmm. Yeah.
And so that's why you can normalize the theory that lives on the lattice and so on.
One other point of view that I've sort of mused about just in terms of scales, if we want to do Starobinsky style inflation, that tells you the size of the R-squared term, which has to be huge, which means actually a light scalar particle. Now, because under renormalization, Weil squared and R squared, they they dance together like a minuet. So there's no reason whether you have one coefficient of that. I mean, I'm going to quote you now because basically on issues of naturalness under renormalization, those two are going to be mixing all over the place. And it's very unnatural to have one of them very large and the other one of a completely different size. So
Well,
it gives you an idea of what you might expect.
You could invoke conformal symmetry in some way to argue away this other term. You have the R square and the remainder, which is an R square term or something.
Yes.
And you could argue away that R square term. We had a discussion before, remember in RHA. But
Yes.
I found it not quite conclusive. I thought that conformal symmetry should be helpful in removing these extra terms.
Mhm.
Or fixing them somehow. That it could be that there's a Y square plus some anomaly which is caused by the higher order interaction, and that anomaly causes some R square term to restore the conformal symmetry or something. In that case, the R squared would not be a separate degree of freedom, but something that just is there to cure the theory of its diseases.
Yes.
But it's not obvious, and I haven't quite understood this.
Well, it's certainly true that there are conformal anomalies, and indeed that those in this context of this discussion have not been very much taken into account. So the Weil squared term, of course, is happy as a conformal theory, but unless you have a maximal conformal supergravity, even
Hi,
that, sorry,
everyone.
that one needs also. Oh, hi, Gia.
Hi.
That theory also needs a very particular matter content. So the conformal anomaly-free theory is very restricted. So indeed, you're going to have an anomaly.
I think, Anubhav, do you have a comment related to this?
Yeah, so I have a comment to Kelly. So I think I absolutely agree with you, Kelly. So there's nothing wrong with you said. But one of the things which we have to keep in mind that just with string theory alone, we cannot solve many of the hard problems. So for instance, if you want to understand very close to what's happening close to the singularity or things like that, string theory will not help us. No way it will help us, because in a time-dependent background, it's really very bad. I mean, very hard to manage it. Mathematically, it's very hard to control them. So in some sense, I think the idea behind what people have been doing is to take it as a tool, not as a fundamental theory, but take it as a tool to see how much can we learn very close to singularity and things like that. So in this respect, perhaps maybe these world-line approaches which people do, it may not be a very bad approach. Of course, nobody is saying that this is a fundamental theory or all these infinite derivative theories of gravities are fundamental. After all, at the end of the day, string theory is the way to go. But I think it's just the fact that it's very hard to control string theory in a time-dependent background also makes it uncomfortable mathematically.
Well, there's also the aspect of
what's your opinion?
Perturbative string theory, of course, clearly is not the final answer. We
the
very much
not,
the non-perturbative aspects of string theory are crucial, and I don't think we understand them properly yet. What they have to do with the question you just raised.
Yeah. So it's in a way, it's kind of like a tool rather than a fundamental theory, in my opinion.
Yeah. So indeed. So that's why I've personally returned to the subject after many years doing supergravity and stuff like that. And more recently, in the vein of an effective theory, and also I find also the links with the asymptotic safety program are also interesting. I mean, this is something, of course, that Roberto has spent a lot of time and effort on. It does strike me that trying to do asymptotic safety within the context of a renormalizable theory has certain attractions, because everything is under much better control.
Actually, I think Alessia wants to say something about this, right?
Yes, so I have really quite a lot of comments on what you, Kelly, said. So step by step. So yeah, you say that Donohue's approach could be partially a solution, but not completely. And I would agree with that, because I would also not be happy with an unstable ghost, because it could be kind of a temporary solution with just shifting the problem. But it is also true that these calculations are based on just one loop result.
Indeed, yes.
And it is already non-trivial that adding one loop results, the ghost of the simple quadratic gravity becomes unstable. So I would say going in this direction might be promising first. And then the point is I would say the question is whether the full effective action will be ghost free or with just an unstable ghost or whatever. So I think that is just a partial result, and it is a proof of principle that adding quantum effects could have a role. I don't think that the unstable ghost itself is a solution to the ghost problem. And
yeah, I liked your talk very much, because you were talking about this electrodynamics or vector theory analogy, and then showing how the progressive decoupling as you go to higher and higher orders. I thought that was a nice point of view, and I guess that's what people call phacons. I never quite understood what phacons were.
No, it is slightly different, because what Anselmi does is to take the ghost of quadratic gravity and say, I don't want it. Okay, so now I've modified my Feynman prescription such that the contribution to the spectral density is 0. Okay. So essentially, it puts the residue to 0 by hand, if you want.
Okay. This is
what I have done instead is different, because I show that if one does performs a truncation and then enlarge the order step by step, as the truncation order goes to infinity, but even at low truncation order, then the residue associated with ghosts or poles that are not in the full theory dynamically go to 0. And this could be a good decouple mechanism, independently of what is the fundamental theory.
Yeah, I've always vector theory analogies because I think they show in a theory that we think we understand, how in this sort of expansion, if you ever decide to go out for lunch and stop your approximation, you've just now invited a ghost. And so what you were showing is that they decouple, depending on how hungry you allow yourself to go. If you go on and on and on, then the coupling goes down. I thought that was a very nice point of view.
Thank you. And yeah, so this was one of the points that I wanted to make. And related to the non-locality business, I think that non-localities could be important at the level of the effective action, but I think one really has to make a difference between the non-locality that arises from integrating out modes or quantum fluctuation in general, and this is what happens at the level of the effective action, and the business of non-local theories that, as far as I understood, the non-locality is introduced at the level of the fundamental action, and that is something that it might be that it works, but I don't understand the motivation for doing that. Because one could have a very nice form factor at the level of the fundamental action, but it doesn't really.
If I can make a comment,
gravity is by definition non-local. I think what Gia pointed out is gravity by definition is non-local. You can't help.
If I can make a comment,
but I don't know this. Yes, Luca.
Yeah, first a comment to you, and then a comment to what Luca said. So what you were saying, I totally agree with you. Basically, first of all, that basically the Nog approach is very nice because it's just telling us the quantum effects maybe can help. Okay, but then to be helped by some non-perturbative physics, because we need to know what happens at higher loop up to infinity, of course, and what it's doing. That's why self-safety can really be tied to what also the Nog is saying. Okay, some kind of complete his work, basically. Okay, I don't know how to say. But then, non-locality also come into the game. Okay. And so it's true in a way that although we are speaking about different things, in a way we are converging anyway to the same problem, because non-locality is needed. Non-perturbative effects most likely are needed. Okay. Perturbative hints are needed. Okay, so we are converging somewhere. Now, regarding the non-local theories that you were mentioning, it's true that we put it by hand, okay, but in principle, we don't make any assumption on the fundamental nature of this non-locality, because in principle, it can be also some emergent non-locality. We don't make any assumption, we just work with the Lagrangian. Of course, then what you assume, it counts, but since we don't have any principle, depends on the point of view, because we don't have any principle.
Yes, but I think it makes a difference, the interpretation, in the sense that...
It changes totally, yeah, of course.
If it is, yes, my point is, yes, you have a nice form factor, but if it is at the level of the fundamental action, the moment that you start introducing quantum fluctuations, that form factor that is super nice, there will be a bunch of corrections, so it is not longer obvious that the unitarity of that comes from that form factor will be maintained once you add all quantum fluctuations. So if that form factor arises from asymptotic safety of string theory or your favorite theory of quantum gravity at the level of the effective action, that's great. Sure. So I think in this sense, non-local theories of gravity in terms of motor building of an effective action that works well in terms of unitarity and phenomenology and so on, it makes a lot of sense. But at the level of the fundamental theory, it is not obvious that then when you add quantum fluctuations, everything will be good as well. So then it makes a difference. The
no, I agree with you. I agree. The interpretation is different. No, only for Anupam, because Anupam sent me a message too. No, I agree with you, Anupam. Depends. I mean, if you start from the word line approach, but even there is a freedom because you need to choose which is the proper time for the word line approach, right? So no, it was something. Yes. Yeah. But
and
you're muted. Yeah. You're muted. You're muted.
Maybe I just very short comments. I absolutely agree with you that non-local theory cannot just come from fundamental point of view, because there are a lot of problems. First of all, when we deal with usual seed theory, we know that we deal with some distribution, but if you want to discuss infinite number of derivatives and the term of distribution, we need to introduce so-called analytical distribution. But in this analytical distribution, we can give a notion of locality. This is a big problem. There are something intermediate, but still, in this case, would be very difficult to preserve micro-locality. So many people, it was made a lot of attempts in 60 in this direction, but still does not work. And if you expect to get, and we really got this from string field theory, this is okay, because this is some kind of effective theory. In some region we can restrict ourselves, but with approximation, that's all. So I totally agree with Alice. Okay, thank you.
Before moving,
before moving, I have a question, simple question about quadratic gravity, local theory.
No, I just said before because there was a comment about like non-locality.
Okay.
So yeah, and then as Anupam was saying, it's true that non-locality also appear in black hole physics, as Gia was saying. But I would distinguish a bit these two non-localities because anyway, in that case, is a non-locality not like in the propagator, but it's just non-locality in the spectral densities. Maybe the two can be related somehow, but in principle they can be different. Okay, and in the black hole case, I think is also more interesting from my point of view because it's something which emerges as a collective phenomenon. You see it like it's exponential non-locality and spectral density related to the black hole entropy basically. Okay, so it's very nice. So it has a very physical meaning. So yeah, that was just the one point. So please, Raman.
Yeah, well, it's my question is about stellar gravity. Well, two stellar. So the thing is, there was some confusion during the workshop about scattering amplitudes in the fourth order gravity. Well, one thing it is the scattering amplitude. If you take two graviton to massless, well, it goes like just like GR, but there are other states as well. There was Bob Holdom commented on this, but I got confused. It was not clear to me. So I mean, what do you say about scattering amplitudes in this theory? Yeah. In your theory. Yeah. It's true.
Sorry, was that a question to me? I didn't understand.
Yeah, it's a question to you, actually. So
sorry, I was typing something. Yeah. Sorry, could you repeat it? I'll be happy to.
I was asking, yeah, repeat, Raman.
No, what is scattering amplitude in fourth order gravity? Because we had a discussion during the workshop, so I think there is some confusion. So it cannot be like GR, right? So I think Shapiro also pointed out, but I want to understand it better clearly. So what is the answer? Is it the scattering amplitude goes like GR or something else?
Oh, I see. Shapiro was saying that the effects of the higher modes cancel out in amplitudes. I found that interesting.
At 3 level, yes.
It's an interesting observation, and I haven't had a chance to really think about it and decide whether I fully agree with it or not. But no, I found that was one of the interesting points of the conference. That's about all I can say about it. I have no.
No, I think there are two papers which agree on the computation about the three level statement. Okay, so I think, I mean, unless they made the same mistake, but they agree on the computation. So I would agree that 3 level, the action is the same as GR. That's what.
And Ilya, you were saying during the workshop in one of the comment of yours, this fourth order gravity in the UV behave so differently, and the scattering amplitudes cannot be like something like GR. So it was unclear at that point. I wanted to ask, maybe if you can elaborate more your point of view on this, would be more clear.
Actually, okay, thank you. I would like to make a general comment on ghosts because we have a few papers about this, and the main result is the following: that we as Kelly said, we were exploring stability of classical solutions with normal C-square term, with the square of the Weil tensor. So, by the way, if you put big R square, coefficient of R square, it does not affect
Sure.
C square by normalization. So it's one detail. So you can keep it separate. You can keep it big without big C square. Now, and we just took different cosmological solutions, like radiation dominated, matter dominated, de Sitter and things like that, and made perturbation of metric, tensor perturbations. And this was done long before us, from 83 by Stravinsky, and we did the same. Then Hawking did the same with Hertog and Riel and somebody else. And nobody ever saw this, regardless this theory has ghosts, nobody ever saw exponential modes, growing modes. Then what happened? When we put initial frequencies of the perturbations of the Planck order of magnitude, then we saw the growing modes there. So my interpretation is the following: if you, in order to create ghost from vacuum, you need to create gravitons with the Planck density of energy. And so if you put initial seed of metric perturbation with the Planck density, then it explodes. Really, you have ghost alive. If you have ghost alive, everything goes to hell. But then we did some work with Patrick Peter from Paris, and we found the following: that everything, it explodes. But if you make this in a very, very rapidly expanding universe, like big inflation, like age of 1.1001 of hub of Planck, then what happens is that frequency enters the equations for metric perturbations divided by square of the A of conformal factor. So what happens is that if universe is expanding, then these perturbations grow exponential, but then they stop growing and start to decay. And this another paper we did recently, which Salvio cited, I think, so is that actually he did completely equivalent work. So that we studied linear perturbations, but in fact this effect is completely nonlinear. We can check it with the Bianchi 9 universe, which is the kind of gravitational wave with zero frequency. Then we saw that even if you go to non-perturbative regime, then the same situation happens. So what I want to say is that you need some restrictions on the filling number of gravitons, okay, which forbids them to accumulate with the Planck density. And this restriction, I don't know how physically explain why this restriction occurs, but this restriction may be violated if the universe is very, very rapidly expanding. Then it is not dangerous.
Can I ask about the context of what you just said? It's very interesting, but there is a kinematical restriction just in terms of Feynman diagrams. So the simplest diagram where an ordinary particle comes in at some modest velocity, it decides to emit a ghost, and then it goes away faster, right? That's that. But that, however, is kinematically prohibited until the incoming particle has an energy of the, or momentum of the scale of the ghost mass. It just doesn't work. But you can have there is a 4-point diagram which there's a split up. Also, a ghost goes out. Then this is kinematically possible. And does your analysis include processes like that where you have multi-particle production?
Well, Kelly, we did not, in these papers at least, we did not discuss diagrams at all. We just made perturbations of
the language
solutions.
diagram, because I saw a difference, so that's why.
Language of diagram, I think up to some extent, yes, because we take into account non-trivial cosmological background. And this non-trivial cosmological background, of course, you cannot reproduce it with 3-level diagrams or even 4-point diagrams. You need all point diagrams, especially cosmological metric. Nobody did it, as we know, okay? But I think if somebody will ever do it, he will need all point diagrams at least, okay? So the answer is the first approximation is that I don't know. Okay.
It'd be very nice to understand this. Is a crucial point. It's very nice to understand this more formally, why it's happening.
Yeah,
like
I have no, I cannot offer this explanation. But I would say that what we found, let's say, where we can find the solution. We can find the solution in some theory, which automatically forbids accumulating gravitons with a Planck density. It can be like Gia said in his talk, it can be a kind of ultraviolet confinement of gravitons and ghosts or something else, I don't know. Maybe forming a bound states with ghosts. We are thinking about this, but without much success, let's say. Okay, but this is a direction of thinking, in my opinion, because otherwise I was doing many different approaches to ghost issue, and I could never get anything except this. Okay, so I believe that there must be some radical modifications in ultraviolet which make this accumulation of ghosts with Planck density forbidden.
Okay, maybe we can hear from. Actually, can you put your paper in the chat, Ilya? Can you send your paper in the chat?
Your paper in the chat?
If you can send your paper.
Sorry, I did not understand.
If you can send your paper in the chat, so we can also have a look. The reference.
Ah, you mean references?
Yeah, the reference to your paper. Yes. If you can.
Sure. I will do it. Okay.
Kia, please.
No problem.
Hi, everyone. You again. So I have a sort of a question comment along this the same line of non-locality and integrating out things. It's slightly different perspective. So this is what I wanted to ask. But maybe it's useful. Can I share a screen for just a microsecond? I can show a formula. Easier. Okay, so do you see this? Do you see the screen?
Yes.
Yeah. So this is okay. We were thinking about these things on some effective non-localities and stuff, and long ago. This is my paper from 2005. From mostly motivated by dark energy, self-acceleration, and this kind of stuff. And from this point of view, modifying gravity at large distances. I mean, the motivation is not so important for my question. But here's what I sort of a little bit continuation of what I was trying to ask yesterday. So here is this equation 1.1. This is a linearized, more general, ghost-free linearized theory of spin 2. Okay, sort of graviton, but not massless. So this is Pauli-Fierz type mass term because that's required by the requirement that there are no ghosts. But I allowed it to be actually arbitrary function of box. And then, okay, so here's this m square. So it could be some power series in box. And I limited myself by alphas that were ghost-free. Actually, the cases that are best understood are when m is simply a constant, that's a massive case, or when it's a square root of box. That's also a very well understood case with full UV a full nonlinear embedding, but it doesn't matter for this question. So basically, what I try to do is the following. So this is a perfectly local theory. This linearized Einstein, etc. So now this theory propagates 5 degrees of freedom. So effectively, you can. So if we think about, sorry. For example, amplitude is given by this, blah, blah, and there is the Shellen-Lemon expansion of the graviton propagator, and it's perfectly local so far, okay? But then there are these extra polarizations, which are basically Stuckelberg fields, okay? So here's the important point. So basically, you can split this theory into, this graviton, which propagates 5 polarizations, just like Pauli field's graviton. You can split it into an Einsteinian 2 polarizations, and the Stuckelberg field, this A mu, a vector, which contains a vector and a scalar. And then you can see immediately that the theory is fully gauge redundant. So H mu nu itself is gauge singlet, it doesn't shift under gauge transformation, but H tilde and A mu, they compensate each other. There is this gauge transformation, and so the theory is gauge redundant. So A mu literally acts like a Stuckelberg. So basically the point is that the extra polarization of this graviton, which is no longer a massless graviton, acts like a Stuckelberg for the original Einsteinian polarizations. Mm-hmm. And then what I did, I asked this question: what happens if I integrate out Stuckelberg fields? Just honestly, go and integrate it out. And so this is what I did. Actually, it's a straightforward, it's a nice exercise. So you can integrate it out exactly. So this procedure is exact because the theory is bilinear. So it's exact to both at classical level and quantum mechanical level. And then you get, for the remaining 2 polarizations of Einstein polarization, you get an effectively non-local theory. So that's what I meant. So therefore, so now somehow the idea is that if you have an observer, so imagine that you have an observer that only interacts with two Einsteinian polarizations. At the linear level, that would be observer with the conserved energy momentum tensor. Because if energy momentum tensor is not conserved, is conserved, at the linear level, this A mu, most of the components of the A mu decouple. The scalar still couples, that is true, but anyway, let me put that aside. So somehow, if you have a theory in which only Einsteinian polarization, if there is an observer that can only probe Einsteinian polarizations, this observer will effectively see a non-local theory, although the original theory is local. So in all the experiments, this person will reconstruct something which behaves as if it's non-local. And so so this is basically, I can stop sharing the screen now unless there are some questions. Anyway, so this was my sort of general question. Therefore, that I have, I don't know what is the answer, and this was also what I asked yesterday. Could it be that every time we see non-locality in a ghost tree, if there is a theory which is ghost free and effectively non-local, could it be that it's always effectively can be understood as a projection of a theory that contains other degrees of freedom? So in this particular case, these are Stuckelberg degrees of freedom that have been integrated out. But so I don't know the answer. So I'm just asking a question. So,
you say that you say that there are 5 degrees of freedom, but there are 7, of course. There's a massless graviton having 2 degrees of freedom, and the massive thing having 5 degrees of freedom.
No, there is no massless graviton here. So here you each. So here at each level. Yeah. So you can do Shellen-Lemon expansion of this. So at each level you have you can think of it as a theory of a continuum of massive gravitons. Of course, at m equals 0 level, I was saying at each level. So at each mass level, you have 5, except at m equals 0. Yeah. So yeah. So you're right. Yes, m equals 0 has 2. Of course, I'm not interested in that one. That's standard. But at massive levels, you have 5 at each level. And so what I did is that, of course, that's well known. I'm not reinventing it. But what I did was to integrate out the Stuckelberg components and write down an effective theory.
You have been hiding the graviton, but it doesn't go away like that. You just you can do that with any theory that you say the effect of a particle is taken into account, but the particle itself not. But it will still show up in the unitarity relations and everything, that you can also generate these gravitons together with the massive particles. So it looks like a mathematical trick, but it doesn't change the physics. The physics
You mean in the full theory?
7
No,
degrees
of course,
of
how can I change physics? I'm not saying it's changing physics. That's precisely my point. I mean, I'm just saying, yeah, no, you are. So in
It's
other words,
my point also that you're not changing the physics. You still have a theory. It actually has 7 degrees of freedom, 2 massless gravitons and 1.
forget about massless graviton, Gerald. Let's take, for simplicity, let's take m squared to be just a constant, just that constant, okay?
Yeah.
So in that case, from the beginning, we are in a theory of a Pauli first massive graviton that has 5 polarizations. Out of these 5, there are 2 normal Einsteinian polarizations, and there are 3 extra, which act like Stugelberg fields. And so my point is that if I integrate out the 3 extra, what remains, the 2, they effectively have a non-local theory. That's obvious, because I've integrated out degrees of freedom that are Stugelberg degrees of freedom. Now, if I have an observer that only interacts with these 2 polarizations, experimentally, this observer will reconstruct this equation, the equation here that is written here. So that will be an effective equation that this observer will reconstruct, because this observer has no other access, no means to interact with the Stugelberg degrees of freedom directly. So in any experiment, if this person is producing only Einsteinian polarization, effectively we'll see a non-local theory. That's what I was saying. Of course, the full theory is, you are absolutely right, obviously. How can I change physics because I have a special observer? So this would be a seeming non-locality. So because of the lack of this observer to access the other polarizations. And that was precisely my question. Whether every time we have some effective non-locality, always can be completed. But basically, the question is whether if I have a healthy non-local theory, whether the healthy non-local theory can be always completed to a local theory by integrating in some Stugelberg-like degrees of freedom or some other degrees of freedom. So that's a general. I don't know the answer to the.
Are there healthy non-local theories? How do you know? Because if you want
this one is healthy. I mean, it's linear theory. I gave you an example. This one is healthy. I mean, it's a linear theory. I mean, nothing happens here. There are no ghosts. Take m squared to be constant. This is a linear theory of spin 2. That's it. There is nothing happening here. Nothing inconsistent is happening here. Of course, it's not describing nature. I'm not saying this describes nature, but it's a toy example.
But Gia, we have a counter example. I mean, a string theory is inherently non-local. If I look it from the worldsheet perspective, it's a healthy non-local theory, and there is nothing wrong with that.
No. I mean, yes. I mean, I'm not. So yes, of course. Sometimes when we say non-local, we put slightly different meanings in statements of non-locality. I mean, yeah, string theory is. I mean, I would. Okay, I don't know if I would say that string theory is non-local in the same sense as this toy model, because in this toy model, because string theory is self-complete. Whatever it is, it's self-complete, sort of, right? At least there is no evidence that it requires yet another completion. But of course, here this theory, this equation, is not a complete theory. It's a part of a complete theory, but it's only part, and that's why it appears non-local. And so that's why here this toy model is just, of course, this is just a toy model, as I said.
Okay, just make a comment, and then we go to Alessio. Sorry, Alessio, just 1 second. I think it's, at least in the string field theory formulation of string theory, there is this cubic vertex which has this exponential of box 5 cubic. Yeah. Okay, and as Alexi was saying that, I mean, this is a bit different. Yes, Alex, 2 days ago, I think. This kind of non-locality is a bit different from the usual locality that you can get when you integrate out fields, or I think the story, maybe as Nuba was saying, string theory and string field theory is a bit different. And I don't know, maybe Alex also has raised hand.
Alex, you raised hand, maybe he wants to comment.
Yeah, but yeah, maybe let's just go in order. We can just see Alessio and then.
May I have some short clarifying comment about this?
Yeah, please, Alex, if it's about this, yes, please, you can comment.
Yes, it's exactly about this. Yeah, I want to understand. Do you say that you have a perfectly local gravity and then you integrate out some vector component as you introduced it, and then you get non-local effect? Is it what you are saying?
Yeah, I mean, of course, it's not a realistic gravity. It's a linear theory. It's a linear.
No,
let's take out.
No, I understand.
So you get
well, but can you just clarify what do you mean when you say integrating out?
Well, I literally integrate out. This is an exact procedure. It's exact to all orders because it's a bilinear. Since it's a bilinear theory, I'm integrating out this Stuckelberg component. Because theory is bilinear, it allows you to integrate it exactly out. And so this is what I'm doing. I'm literally solving equation for Stuckelberg components and then plugging it back into the action. And that's a legitimate procedure because action is bilinear. And so that's what I'm doing. Yeah.
But since we understand that initially it should be a gauge degree of freedom, do you somehow count that determinant will change in your path integral?
Well, it's exactly as I said.
Out?
So because theory is bilinear, in this particular class of theories, actually, it's interesting that you can do this procedure exactly. And there is no problem with gauge redundancy. As you can see, the final theory that you get is it has exactly the same gauge redundancy as the original theory. So therefore, it's an example in which we are lucky. We are lucky because this allows us to integrate. So gauge invariance is maintained at each point. So there is absolutely no problem. So yeah, so as I said, I mean, I don't want to confuse terminology because I don't even know if I should call this theory non-local, the one here. It looks non-local because of course it contains 1 over box, and so if I'm an observer that interacts only with this H tilde component, I will naively get confused because I will think that there is some non-locality in here. But this would be a fictitious non-locality because it's simply a fact that this observer doesn't have access to other degrees of freedom of the theory. And that's the only, it's an artifact of this limitation of an observer. So, yeah.
I see.
Alessio, maybe you want to
Yes, so originally when I raised my hand was like to make a comment to one of the comments of Kelly, but first let me say something about Gia's argument. So first, this is what I meant at the beginning when I was saying that eventually the fundamental theory can be local and one instead has no localities at the level of an effective theory once you integrate out degrees of freedom or resummable quantum fluctuations. And now I don't, I'm not 100% sure that I get your question because so if I get your question correctly, then the answer would be yes, because even in the standard model, if you start with quantum electrodynamics plus some matter, say fermions or scalar, and you integrate out that degree. So the action in that case would be local, right? But if you integrate out your matter degrees of freedom, you get an action that is non-local, and that's in fact these logarithmic corrections that comes from the by integrating out degrees of freedom. So I don't know if it is related.
I think that when we integrate out this,
good example. Yeah, so it's also a good example. That's also an example when we integrate out massless degrees of freedom and write down effective theory.
Exactly.
If I write down effective theory of the part of the degrees of freedom, it would naively look non-local. So yeah, it's the same point. It's from this exactly the same thing. The only difference is that here it's a little bit more sophisticated because I'm integrating out Stuckelberg degrees of freedom.
Yes, I agree that in that case it's a bit different, but the concept is the same, right?
Yeah, I fully agree. That example also would fit in this category. My question was, I don't know the answer. The question was whether every time you have, let's call it healthy non-locality, every time the healthy non-locality can be completed to the local theory, which is more fundamental. This was my question.
I don't think it is. I would say that it is not a one-to-one map. I mean, if you integrate out the degrees of freedom, you get non-locality. But if you have an healthy non-local theory, it is not obvious to me that the fundamental theory will be local.
No, to me also, it's just a question. I mean, it's a
okay.
question.
And so I don't. Okay.
But it would be nice to know the answer.
Sure.
As I said yesterday, I mean, it would be really, at least, I mean, I would find it fascinating if there is a healthy non-local theory, ghost theory, which is not effectively understandable as a result of integrating out degrees of freedom. To me, that would be really something extraordinary.
Yes, of course. But that's in fact what I was saying at the beginning. Can I? That's what I was mentioning at the beginning. That eventually, I mean, your favorite fundamental theory of gravity could be local, and then you don't give up a locality at the level of the fundamental theory, but you get a non-locality at the level of the effective action, effective field questions, or whatever you want to see that.